Hello, I welcome you all. The problem reads I draw the shear and bending moment diagram for the beam ABC. Note that there is a pin at B. The problem is coming from the Engineering Mechanics and Statics textbook, 13th edition by R.C. Hibbeler. So we have a continuous beam here that is fixed at A. We have a pin at B and a roll at C. So we need to draw free body diagram, but we need to dismantle AB. Separately we draw and BC. We'll start with BC. So that we come and work on AB later on. So there we go. We have A there, this is B, and then we have B there, and this is C. Both are loaded with a distributed force. All right. And also this one. Okay, and this W, and this W. All right. We have the equivalent for both. Since the lengths are just more or less the same. The length are the same, L over 2, which is just 0.5 L, and so is the other one, 0.5 L. At A it is fixed, so expect a reaction AY, AX, and a moment MA. And then at B, since I'm starting with at C, I only have a roller CY. Okay, at B, I have BY like so. Doesn't matter which one you start with, I just wanted to start with B for this other beam, BX, and then here it will just be opposite BY, and then BX. Again, doesn't matter which one you start with. An equivalent force there, okay, is going to be equal to W. This is W, so it's W times 0.5 L. So this is 0.5 WL when we multiply the two, and so is this one is 0.5 WL, and it's going to be acting at half the length of the loading, which is going to be equal to 0.25 L, and so is this one here. This is going to be equal to 0.25 L, right? So we'll start with beam BC. We'll apply the equations of equilibrium quickly, and then later on move to AB. So let's start with B. Summation of forces about point B equal to 0. All right, what we have? We have minus 0.5 WL times 0.25 L. And then we have plus CY by 0.5 L equal to 0. L and L, and L and L goes. CL therefore is going to be equal to 0.5 and also 0.5 goes. So what we remain with therefore is 0.25 WL, okay, which is a quarter, right? And that makes sense. It makes sense. So we are saying here is going to be equal to 0.25 WL. Okay, then summation of forces in the y equal to 0. What do we have? We have By minus 0.5 WL plus Cy equal to 0. We've already calculated what Cy is, and if we do so, our By therefore is going to be equal to we have 0.5 WL minus this one, or minus, yes, so when they go the other side, it's 0.5 WL minus Cy, which gives us just a 0.25 WL, okay, which also makes sense. And then we know the other one, of course, summation of forces in the x equal to 0. We know that we don't have loading in that direction, therefore Px is equal to 0. Alright, so we found By, which we are just going to replace. We know what By is. It's 0.25 WL, which is the same as the other one there, Cy. cy is the same value also, because um 0.25 WL. Alright, so our by here is 0.25 WL. Alright, this is equal to 0, and so is the other one. So now we are coming to this part. Let's take moments about point A. So summation of moments about point A equal to 0, and clockwise being our reference. So what do we have? We have minus 0.5 WL by 0.25 L. Okay, I just create a boundary here, and I also create a boundary here. All right, up to somewhere there. Okay, so 0.5 L, and then we'll have minus BL by 0.5 L, and then we are going to have plus MA equal to 0. Is that so? Let me check. Okay, by, of course we know what it is. So this by is already calculated as 0.25, right? Great. Therefore, our MA is going to be equal to, let's do the calculation, 0.5 by 0.25 and 0.25 and 0.5. So this gives us a 0.25 WL squared. All right, great. Then we have summation of forces in the y equal to 0. What do we have? We have AY minus 0.5 WL, okay, and then minus 0.25 minus PL minus BL equal to 0. Again, we know what BL is, therefore AY is going to be equal to, so what do we have? We have 0.5 WL minus 0.5 WL minus BY, which is 0.25. Therefore, this gives us AY equal to 0.75 WL. So it's like we are done with this, and then summation of forces in the x, direction, we know that our AX is just going to be equal to 0. So let's replace these reaction forces. So our AY, we are just from finding it, is going to be equal to 0.75 WL. And then our moment is just going to maintain in the same direction. Our support moment is going to be equal to 0.25 WL squared. All right, great. So I'll need to delete this so that we move on. Okay, there we go, like so. All right, so now with this information, what we need to do now is to, let's label our points of section point 1 and point 2. So I'll start with sectioning AB, like so. And once I section it like that, let me draw a small free body diagram. It has a load there of 0.75 WL. It has a moment of 0.25 WL squared. And then we have a uniformly distributed load of intensity W, and it's going to be positioned at the mid center of the loading itself. And this, since this And mind you, we are moving from this direction to this. Okay, we are using the left hand side section, right? So this loading, this is x moving, this is x. Okay, let me write it properly. You can see it, this is x, and we are moving from the like so. And therefore this is this loading is going to be equal to w times x, which is just wx, and it will be acting at half the length of x, which is 0.5 x. And this point here we called it 1, so I expect some internal forces there, v1 and m1. Of course, we know that the normal force is going to be equal to 0, so there is no need to indicate it. So let's apply the equations of equilibrium. This point at the very end here is A. So let's say summation of moments about point A equal to 0, and clockwise being our reference. So what do we have? We have wx times 0.5 0.5x, this is positive. And then we have minus 0.75 WL times what? Times x, and then we have this support moment, which is 0.25 WL squared, and then we have finally the moment that we are looking for, which is m1 equal to 0. Therefore our m1 is just going to be equal to our m1. Let's check what this is equal to. Our m1 will be equal to minus 0.5 wx squared plus 0.75 WLX, and then minus 0.25 WL squared. Yeah, so something like this. So let me move this a little bit back so that I just have some space. Okay, up to maybe somewhere there. Right, let me just go through again. So we have m1 is equal to minus the 0.5 wx squared, and then plus 0.75 WLX, and then later on minus. Yeah, okay. So this is fine. This is fine. Let's go to the shear summation of forces in the y equal to 0. Okay. What we have? We have 0.75 WL minus WX minus V1. Anything else? We only have 3 forces, so this is equal to 0. Therefore, our V1 is just going to be equal to, what is V1 equal to? Is equal to minus WX plus 0.75 WL. Great. So this is about it. Let's draw another section. We'll section this at this point, and then we'll be moving from there to there. We are using the right hand side section. Great. So let's draw a small one. There we go, something like this. This point is C. We have this force here, which is 0.25 WL. We have the loading, the uniformly distributed loading of intensity W. And then we have this length, which is X, and we are moving from this direction like so. We have the intensity, I mean the equivalent force, which is W times the length, which is just WX. And then it's acting at half the length of X, which is just 0.5X. And then here, this point is 2, so we expect our V2 like so, and our moment M2 like so. Great. So let's apply the equations of equilibrium. Summation of moments about 0.2 equal to 0 like so. What do we have? All right, we have minus Wx, this is clockwise, times 0.5x. And then we have plus, this is anti-clockwise, 0.25 WL times x. And then we have minus M2 equal to 0, right? So Wx by 0.5x, which is clockwise, then 0.25 WL times x anti-clockwise, and then minus M2, which is therefore M2 is going to be equal to minus 0.5 Wx squared plus 0.25 WLX. That's about it. Let's find the shear. Summation of forces in the y direction equal to 0. What do we have? We have minus Wx plus 0.25 WL then plus V2 equal to 0. Great. Therefore, our V2 is just going to be equal to, our V2 will be equal to Wx minus 0.25 WL. Right. We are done. We are done with these sections, but we are not yet done with the problem. So we have these two sections, V1, V2, M1, M2, okay, for the interval A, B, and BC. So let's go ahead now and just start putting this data into, we organize it in this manner. All right, like so. And then finally another one like so. Right, just lift it a little bit, maybe we'll bring it here. Okay, so there we go. So we just need to again redraw this information here. We have A, we have a hinge at B, then we have C. We have a moment here, which is 0.25 WL squared. We have a reaction force 0.75 WL. We have one also at C, which is 0.25 WL. Then we have this distributed force. We have this distributed force of intensity W. We have this distributed force of intensity W. And then we have the dimensions. Dimensions are given as follows. Something like this. Something like that. Okay. This one is equal to 0.5 L, and so is this one. Great. So this is our shear force diagram, and this is our bending moment diagram. All right. So 0 there, positive up, negative down. 0 there, positive up, negative down. Right. So let's start the work. So let's find the values in the interval AB for V1 at x is equal to 0 and V1 at x is equal to 0.5. So let me use red. So V1 at x is equal to 0. Let me also make this demarcation here to just show that we expect some change of behavior, especially for the moment, because we know that a pin cannot transfer a moment. A pin will only transfer forces in the horizontal and vertical direction. Okay. So there we go. So V1, we expect V1, we have this equation here. This is what we're using. What is V1? So we are moving from A to B. What is V1 at x equal to 0? Of course, you expect V1 to be equal to 0.75 WL. Great. And what is V1 when x is equal to 0.5 L? Okay. 0.5 L, what do you expect? So we have V1 0.5 W by 0.5 L plus 0.75 WL. So what do you have? That's 2.5, right? 0.75 minus 0.5, that's 2.5. So we have a positive 2.5 WL. All right. We are done with this part. Let's go to V2 at x is equal to 0. I mean at x is equal to 0. Mind you, we are moving, in this case, we are moving from C to B. It's very important. The other side, we are moving from A to B. All right. Okay, so we are moving from C to B. Please take note. Our V2 is this one here. So when x, okay, is equal to 0, at C, we expect a value of minus 0.25 WL. And then when x is equal to 0.5 L, okay, so let me calculate it quickly. So we have W by 0.5 L minus 0.25 WL. Right, so when we do the subtraction here, it is just half, right? 0.5 minus 0.25. So it becomes 0.25. It becomes 0.25 WL. All right, so let's do the plots for this one and then we move to the moment side. Great. So we have all the values here. So what we need to do now is to do the plotting. So in the interval AB at A, when x is equal to 0, being told we are going to have a value of 0.75, quite high. I think that's the maximum. So we expect a value like so. Okay. Okay. All right, let me just wrap that. So let's say we are going to expect a value like this. Okay. And then at B, to the left of B, so this point here, to the left of B, you expect 0.25. So let's say I'm not drawing them to scale, up to there, somewhere there. So let me connect the 2 points. So we have this behavior like this, all right? Because when you look at V1, okay, V1 itself is a linear function, right? With a gradient that is decreasing. So this point here we've been told is this is 0.7 WL. Then this one here, it is 0.25 WL. Great. So found for this one, let's go to the section or the interval BC. But we are starting from C going to B. So at C, when x is equal to 0, we have a value of point a negative 0.25 WL. Okay, and then when x is equal to 0.5 L, we have a value which is that one there. So we're going to have this behavior like this there. It's also a linear function. If you look at W2, it's also a linear function. So it will be a straight line from that point to there, something like that. All right. Like I said, I've not drawn them to scale. But we are going to have something like this. So this is positive shear, this is negative there. All right, so this is what we are going to have, like so. And like I said, the joint, the pin is able to transfer shear. Okay, so at B we expect the same shear, okay, either coming from C to B or from A to B. All right, I think we are done with this one. Let's go to the moment. We go to the moment. For the moment, we are going to expect a polynomial of degree 2 for both cases, right? Or quadratic. So first, let's find the values at x equal to 0 and at each boundary at A, B, and C. So let's start with this M1. M1 when x is equal to 0, what do we have? Our M1 is this one here. Okay, our M1 is this one here. When x is equal to 0, we are going to have a negative moment there because it's fixed, right? So we expect a support moment, negative 0.25 WL squared. So we expect that moment. And then when M1 is equal to, when x is equal to 0.5 L, we expect, what do we expect? Let's get that equation and do the calculation. So M1 at 0.5 L, we expect minus 0.5 W by 0.5 L squared plus 0.75 WL by 0.5 L minus 0.25 WL squared. Okay, let me do the calculation. Minus plus. All right, so we have minus 0.5 times 0.5 squared plus 0.75 0.75 by 0.5. All right, and then minus, this one was plus, started with minus, right, plus 0.75 by 0.5 and minus 0.25. All right, so we have, this is going to be equal to 0, and that's what we expect because a pin does not transfer moment. Great. So 0. Great, we expect that. So we are done with these two parts. Let's go to the other part, that is interval 2, which is from B to C, but we are starting from C going towards B. So what is our M2 when x is equal to 0? We are using this equation here. Okay, the equation is clear. We just get a 0 when x is equal to 0 at C. Okay, and then M2 when x is equal to 0.5 L. All right, what do we get? We can plug it in there so that we see. So M2 at 0.5 L equal to, what do we have? We have minus 0.5 W by 0.5 L squared plus 0.5 to W L by 0.5 by 0.5. Okay, by 0.5 L. Right, this one also just supposed to give us 0, and it looks so 0.5 by 0.5 squared plus 0.25 by 0.5, 0, and that's what we expect. Okay, so now let's draw the moment, the bending moment diagram. But before we do so, let's find this length where shear is equal to 0 in the interval BC. Okay, so we can use the shear equation V2. Okay, that we calculated. V2 is equal to Wx minus 0.25 WL. So at this point where the shear line crosses the x-axis, we expect shear to be equal to 0, and therefore we are able to calculate the value of x, which is measured from C towards B. So this becomes equal to 0.25 WL, 0.25 WL divided by W. Then this is equal to 0.25 L. So this is 0.25 L. Right. So now let's draw the moment diagrams. So when you look at interval AB, this is a cantilever beam, okay, with a concentrated load at B. All right, that is what it is. Okay. So it's like a cantilever beam with a concentrated load at B with a distributed load from A to B. All right. And then interval BC is a simply supported beam with a distributed force. Okay. So this is how the moment diagrams will also look. They will just be more similar to AB, a cantilever with a point load and the distributed load, and then BC is more of or it is a simply supported beam. So we have we've done these values, or we calculated the moments considering the boundaries, which are A, B, and C. So from A to B, when x is equal to 0, we calculated moment to be minus 0.25 WL squared. So let's indicate this value maybe somewhere there. So this is the value we calculated when x is equal to 0. So we are moving from A to B. Okay, and then M1, when x is equal to 0.5 L, it is equal to 0. And then when we look at the function that governs M1, okay, it's a polynomial of degree 2, all right, and it's going to be it's going to be in this manner. All right, so let's draw it. It's going to be something like this. All right. Okay, something like this. I may not have drawn it well, but it's going to be something like this. All right, so we have this maximum point, which is 0.25 WL squared, and this is a negative moment. All right, so beam AB will have the maximum moment from the support itself. The moment will be reducing slowly until it becomes 0 at B. Okay, and then for the interval BC, which is also just like a simply supported beam, and we are moving from C to B, and at C, when x is equal to 0 at C, when x is equal to 0, M2 is equal to 0. And then as we move to B, when x is equal to 0.5 L, M2 is again equal to 0. And when we look at the function that governs M2 again, it is going to open again like this. All right. Okay. So if we started from C, okay, we have something like this, like this, like this, like this, like this. Okay. All right. All right. I cannot be that very perfect, but it's something like this. And then I have my maximum point in the span BC, which is equivalent to a simply supported beam at this point. So what we are going to do is we can either use this, okay, or we can use this, all right, to calculate the value of this moment, right? Because we know that the area under the shear diagram, okay, gives us the moment, right? Remember? And we know the maximum moment for a simply supported beam, right? Simply supported with the distributed, remember, WL squared over 8, right? And it's the same value that we're going to get here. But you need to remember that the L is 0.5 L, all right? So it will give us the same value, all right? So I'll not use this, instead I'll calculate using that, but it gives us the same value, right? So let's find the area under the shear diagram, and I'm using this portion here, all right? So maximum moment in the interval BC, this is going to be equal to half times the length, which is 0.25 L, times the height, which is 0.25 WL. Therefore, this gives us 0.5 by 0.25 by 0.25. This gives us 0.03125 WL squared. So this is the value here. This is 0. Let me use red. All right. So it is 0.03125 WL squared. All right. Write it properly. 0.25 WL squared. So that is the value, and the moment there, of course, is positive. Okay, something like that. Right, I guess we are done, and I hope the video was helpful. If it was, give me a thumbs up, like my video, and continue subscribing. Bye bye, and see you in my next screencast.